I guess I don't need to record yet because we still have 6 minutes, but oh well. Guess I'm just gonna. So I was overhearing some of us are coming from 304, some of us are coming from 301. Show of hands, who's coming from 304? Okay. And then I guess everyone else is coming from 301. Cool. Um, who did y'all have 301? If y'all who did we have 301 with?
Uh, the people who just did it had
Buffy? Buffy?
yeah,
Okay.
and then Fiorina.
Fiorina for the people who had it. Okay, cool. Um, I'm mostly just curious because I think reactor analysis is funny because at least when I took 301, dating myself a little bit, I did my undergrad here, and when I was here, Dr. Adams was still a professor here. So I was one of the last undergrads that had 301 with Dr. Adams. So I don't know if I mean, he is definitely just on another level in terms of he's like the next evolution of human beings if you've ever met Dr. Adams. So learning from him, I find a hard time like seeing where 301 ends and where 304 begins because a lot of the material is very similar. So hopefully what that means is that no matter if we no matter where we're at least the way that I set up the course is that we're gonna, at least this first lecture is mostly just review of a lot of 304, sorry, a lot of 301, so that we're kind of all on the same page in terms of like terminology, definitions, things like that. And then hopefully it's a pretty seamless transition into the 304 material. But I'll just wait a couple more minutes and then I'll actually get started. If you came in and didn't grab the things up front, I just have I printed out the first homework for you, and then I printed out the lecture slides because I wasn't sure if we were going to be able to access them in advance or not. So if you didn't see the email that had the PDF of the lecture slides, there's a hard copy of the lecture slides up here for you. And then I printed out the first homework. That's going to be due in 1 week.
The homework will be accessible online soon.
Yes, yeah. Right. Good point. I'll make a note for myself to send out an email because I don't have, oh, so if you have access to the Google Drive, I believe the homework assignment is there too. But I'll talk about that as well because yes.
What's your preferred way of us streaming?
That's going to be on Canvas. I don't have the Canvas set up yet. But it will be set up by the time y'all are going to be turned, like the due date for that first one is June 3rd at midnight. So Canvas will be set up so that you can submit that. Apologies for not having it set up yet. This is my first time teaching here, so I'm still getting used to the systems and things like that. If you're just coming in, thank you for being here. There's a couple handouts up front, copy of your first homework and then the lecture slides. If you weren't able to access the lecture slides, there's a printout for you. Alrighty. Would y'all mind, I guess, it's fine. Good morning, everybody. Howdy. Thank y'all for being here. My name is Sean Simonian. I'm going to be your instructor for reactor analysis. Yeah, so thank y'all for being here, and let's just get right into it. Y'all have never met me before, probably. So hi, I'm Sean Simonian. Um, I am a current PhD candidate here at Texas A&M. I'm going to be graduating in about a year. I am from Austin. Those are the places I went to school. Um, I was a very bad high school student. I did not know what I wanted to do when I left high school, so I went to ACC. I spent Austin Community College. That is where I figured out that I wanted to do engineering. I transferred to A&M. I took some time in between my bachelor's and becoming a PhD student. So after I graduated, while I was in school, I was a tutor at ACC. Once I graduated, I was trying to find engineering jobs, and 2018 was a very bad time to be graduating with a degree in nuclear engineering. So I think the market for y'all right now, it seems a lot more optimistic than it did whenever I was graduating. So no industry jobs that I could find, but I had tutored. I really liked the idea of teaching. So I wanted to see like how would I do with that? So I was a high school physics teacher for 3 years, 2019 through 22. So you guys were in school during the pandemic. I was a teacher during the pandemic. Um, Different struggles, but that was hard for a lot of people for a lot of different reasons. It made me realize, being a high school teacher, that I really liked teaching, but high school teaching was not really for me. So I came back to A&M to get my PhD, and here I am. So I'm a grad student under Dr. Mark Kimber. Y'all might have had him for some classes. My research is in thermal hydraulics, computational fluid dynamics, systems analysis. So I publish papers about coal to nuclear conversions. I publish papers that are more system level analysis of the molten salt research reactor that we're working on. And then I've done some CFD work as well. So I do a little bit of everything. And the reason that I wanted to get a PhD is because I wanted to be a professor. So I'm really excited to be here to be teaching y'all for my first college class. So hopefully it goes okay. Whoops. Okay, so overview of the syllabus. I didn't print out the syllabus because I assumed that nobody really cared to have a printout of the syllabus. But the syllabus is online, so I was just gonna pull that up real quick, talk about a couple things that are important here, and then we can get into our first lesson. So basically, 304 is your last kind of neutronics course, the second semester junior level neutronics course. We are going to cover a lot of really fun stuff. The idea basically by the end of this course is that we are going to have a really solid understanding of how and why nuclear reactors work. And we're going to be able to both be at a point where we can at least do basic reactor design, as well as some a detailed understanding of how and why a reactor might not work and how and why a reactor might go wrong. So part of like maybe the pitch for this class is like, by the end of this class, accidents like Chernobyl, Fukushima, these kinds of things, we'll have the knowledge both to understand how and why they happen, but also get some insights into like maybe how to make that not happen in the future. So that's kind of the goal for the course. Our lecture is Tuesday, Thursday, 10 to 11:50. I don't know if y'all have had a class that does what I am planning to do, but basically every Friday I've rented out the auditorium downstairs, the second floor auditorium. So that's going to be like open office hours where if you guys have questions, we can go over those questions. But also I'm planning those open office hours to be very structured. Every one of those Friday sessions will basically have like one big kind of exam-like problem that will work individually, will work in small groups, we'll work it together, so that we're getting practice with the kind of longer problems that maybe we can't go through in a lecture. So those sessions are entirely optional. They're for your benefit. Yes, question.
Will you record those as well?
Probably not. Those are going to be more like not teaching like this, but like on the whiteboard kind of thing. So it'll be harder to like do a decent recording of that, I imagine. Um, I will post the problems that we go over. But yeah. So that first one is going to be this Friday, 2 to 3:30. So we know prerequisite stuff. Um, these are the learning objectives. Um, in terms of me doing the office hours that way, as a grad student, I don't have my own office. Um, that office M104 is like a grad student debacle. We could just say. So like if you do need one-on-one help, sending me an email and then scheduling that in advance is better than coming into the office just because the office is very crowded. So if you need help, I'm here because I like teaching. I want to help you guys. But in terms of making that happen, sending me an email and organizing a time is going to be a lot better. In terms of things that you want to know about, every lecture, I'm going to provide blank slides that we're going to go through in class. The textbook that I'm going to be following is Dr. Svedkov's notes. That and the recommended textbook are both provided in a Google Drive for you. And I'll talk about that Google Drive in a sec because there's a bunch of stuff there that you're going to want to know about. In terms of the grading policy, we're going to have homework, we're going to have quizzes, we're going to have 3 exams. So that is how the assignments are broken down. In terms of the scoring, it might be different to what you've seen in other classes. I'm going to set every segment up with a range of values such that your final grade, I'll pick the weights to help your grade the most. So maybe we do good on the quizzes, but we don't do good on the first exam. So like if you do bad on one thing, you won't really be punished for it because that will just end up being weighted lower. So that's the whole idea by that normal grading scale in terms of A, B, C, and D. We are going to have a weekly homework. I printed out a copy of it for you today. The idea is that at least my hope would be that once we get the homework and we've had our first lesson, I leave you guys with enough. I've left you with the ability to be able to do a lot of that homework. And then by the second lecture, we'll have basically covered everything that's on the homework. And then, so that's the hope. My feeling or my guidance would be after class, start the homework is, oh, question?
So what you're saying is, by the first lecture, we'd be able to know most of it. By the second lecture, would that mean, for example, there's the 2 lectures on this homework, right? Would
Yeah.
that mean like, or if we just finished lecture 2, we'd be able to do most of it, and then by the end of lecture 3, we'd be able to do all of it?
By the end of lecture 2, you'd be able to do all.
Okay.
Yeah. So
We don't want lecture.
yeah, I mean, a lot of the first homework is really just general review. So like yeah, that is how that is what to expect. I have some guidelines in terms of how I'd like the homework to be submitted, just in terms of like organizational things. All of those guidelines are right here. And I have an example on the Google Drive of one of my homework assignments so that you could look at that and make sure that you're if you're following that format, then you're going to be great. In terms of quizzes, basically every lesson, like except for this one or like a lesson where we have an exam, expect a quiz. Expect it at the beginning of class, like first 5 or 10 minutes, depending on the, if it's a shorter quiz, it'd be 5 minutes. If it's more involved, it would be 10 minutes. Those are going to be closed book and closed notes and no calculator. So that's just what to expect. I think that you will, it might sound scary now. Try not to be like overwhelmed by the thought of having these kinds of quizzes. Hopefully what you'll see after the first couple is that it's mostly like a check your understanding from the lecture and the homework. So as long as we're staying on top of what's covered in class and we're doing the homeworks, the quizzes should be relatively easy. The hope is the two lowest quizzes will be dropped. So if you have a bad day, if you end up missing a class, those the two quiz grades will be dropped. We'll have two midterms and a final. Those are all scheduled, and I'll show the schedule in a second. Similar story with those midterms. They're going to be closed book, closed notes, no calculator. We will practice working problems in that style so that we are hopefully getting comfortable not relying on a calculator for the stuff that we're doing. So that's just what to expect for those things. And then the final exam will be similar. Similar in terms of the format. This is the homework policy in terms of late work. So you basically have point deductions for the first day, and then you have point deductions for the second day, and then any day after the second day, it's the same deduction as long as you're getting it in by like the end of the semester. My hope would be that we're staying on top of the homework, because that is the homework is kind of how y'all get confidence in solving the problems. And I guess this is kind of like a follow-up, which is about the use of AI. I know that a lot of us are probably using AI. I've used AI. One of the things that I want to stress in the course and just in general is like thinking carefully about when we do use AI and when we don't. One of my concerns, like one of my personal concerns for myself, is I don't want to be outsourcing my critical thinking or my creative thinking to a machine, because those are the things that like make us human. And if we outsource that to the computer, then that kind of takes away a lot of the fun and a lot of like the meaning for the work that we do. Also, there's this paper that's cited by M. Gelrich from 2025. It's a very recent paper, and they talk about the phenomena of cognitive offloading, which is a consequence of if you're using AI to answer questions for you without thinking about it, then you're um, you're dulling your critical thinking abilities. And what they're finding, it's a similar thing with Google, where like because we rely on Google so much, our short-term memories have deteriorated. Like I remember growing up before cell phones where you had to like memorize phone numbers, and I don't have to do that anymore because I have a contact list in my phone. So like there's some things with technology that I think it's a useful trade-off in terms of like losing maybe some short-term memory and memorizing like numbers that you can just look up. You don't have to do that. But in terms of the critical thinking, in terms of like those kinds of things, the gist of it is when you're using AI, try not to use it to like do the homework for you. Because ultimately you're just hurting yourself when you do that. You could get a passing grade by using AI to copy every homework problem, but it's not going to help you on the quizzes. It's not going to help you on the exams. When we get into like the workplace, what you're going to find is that at least what I observed whenever I like got my first real job is there's the thing about imposter syndrome, where like you get to this point and then all of a sudden there's a lot of responsibility and onus on you. And when you get to that point, even if you've done all of the work yourself, there's still going to be this sense of like, am I good enough? Do I know what I need to know? Am I supposed to be here? And I can't imagine how worse that would be if I went through a class or like a lot of my degree using AI to do the work for me. So that's just my long-winded kind of talk about AI. I would really encourage you guys to use it to make your work more efficient, to do things that are not like cognitively or critically thinking demanding, but like if you've got a table of data and you need to convert it into an array in Python, that's an awesome thing to make ChatGPT do for you, because it's just monotonous copy pasting. Those kinds of things, ChatGPT is great. Having it do your homework, I would very advise against it. In terms of homework, you can use electronics like Excel, MATLAB, calculators. I'll let you know in a problem statement if you're supposed to be doing it by hand or not. But basically on homeworks, technology is more appropriate. Exams and quizzes, we won't be allowed to use it. So I'll hopefully get you guys trained to solve problems in both ways and be able to recognize when a problem is supposed to be done symbolically. And we'll practice that and hopefully we'll feel confident about that. So the next couple of things, this is a big table that basically shows you, this is everything that's covered in this course, kind of chapter by chapter and section by section. These are how things are outlined in Dr. Svedkov's notes. The other like optional textbook is Duderstadt and Hamilton. This is an optional textbook, so like sometimes you might read a set of notes and you might have a hard time you might just have a hard time with the material. Maybe it's not written in a way that you can appreciate, or maybe it's not written in a conversational tone. I know that like Spekhov's notes are very detailed, but there's no filler, there's no fluff. It's all math, it's all details. Whereas other things might be more conversational. They might present the material in a way that's more easier for you to understand. So that's the whole point of me providing Duderstadt and Hamilton. It's another resource that we can use so that if we're not liking one explanation, we can go to another one. So that just kind of lets you know the general, like what the class is going to look like. Also, the very last column is just what homeworks are going to be covered on from each topic. And then this is the general kind of calendar for assignments. So each homework assignment, each exam, when it is assigned and when it's due. So this is not set in stone. These things might shift around here and there. If anything does shift around, I'll let you know. But that's what to expect for now. Everything else is kind of just general, basic starting a class stuff, university policies and things like that. So the rest of this stuff is here for your information. And yeah, I think that's everything that I really wanted to say about the syllabus. Does anybody have any questions about any of that before we move forward? Yes, sir.
Are you good with Python and just will you be able to help us coding? Coding stuff?
Yeah, I know Python. Python is my preferred language. So yes, to the extent that any problems require coding, if you're doing it in Python, it'll be easier for me to help. Yes.
For the homeworks after the due date, post the solutions.
That is tricky because, right, so it's either one or the other. Like it's either there's no late work policy, and then if you don't turn it in on the deadline, there's no submission, or because I can't, if I do it both, then there's going to be weird stuff that happens. So I'm more inclined to do it this way. I will grade your homework and I will let you know if you're getting the problems right whenever we're grading them. So in that sense, like you will be getting the feedback. Yeah. Yes, sir.
Would you be willing to post the solutions?
So I'm not going to post the solutions. I'm not going to post the solutions to homeworks, and I'm not going to post the solutions to exams, but like I will give you guys feedback on your individual homeworks. So from the individual feedback, that should be enough to know. I mean, that'll tell you exactly like which ones you got full credit on, which ones there was a mistake. When I'm letting you know where there's a mistake, I'll point that out for you. And then if there's more questions from there, that's just a general, that would be something that like setting up office hours. If you are missing points on something and you're unsure why, that's definitely something to like let me know about, set up office hours, and we can make sure that if we did lose points, that we're knowing why and that we won't make the same mistakes on an exam. Cool. I mentioned that Google Drive, so I guess I'll just pull that up real quick. All of us should have access to this. For me, it shows up in shared drives, and then it's called nuclear reactor analysis. Here is where I will, instead of using Canvas, I'm mostly just going to rely on this Google Drive. Canvas is just going to be for submitting assignments and then posting grades. This is where, for example, if you need an electronic copy of your first homework and any other homeworks, they'll be there. Lecture presentations. I will post. This is my first time teaching the class, so I am still planning and preparing the class. I will make sure that you're getting your week's lectures at the start of the week, but I can't provide you like all of the lectures because I haven't made all of them. So that's where you can find your lecture notes for the start of class. This resources folder has Svetkov's notes, it has Dr. Adams' notes, it has the Duderstadt book, it has the first chapter of the LaMarche book. That one is very useful for the first homework. There's discussion of magic numbers and magic numbers of nuclei. I think the chapter 1 discussion there is really good for that, and it's pretty short. It's not, I think it's like maybe 10 or 15 pages. And then the thermophysical properties for materials is just, it's an IAEA document that has a lot of material property. That's just for your reference kind of thing. So class is mostly structured based on Svetkov's notes, but if you're looking at a topic and you're like, I don't feel like this is explained enough here, I would highly recommend taking a look and trying to see if that is covered in Adams' notes or in Duderstadt. Adams' notes are my favorite, so that's going to be always like, if I'm trying to understand something better, Adams is like the first place that I'll check, because if the explanation is there, it's going to be like the best explanation for that thing that you've probably seen. So I really like Adams' notes. But yeah, this is the homework example that I was talking about. So this is like an example of what the cover sheet could look like. This is an example of showing the problem statement, showing all your work. And then if your problem's continuing on to a next page, just making a note that you're continuing the problem, and then boxing your final answer. And so generally, those guidelines that I put on the syllabus are followed here. So if you have a question about something, this is a good document to take a look at. This is for a heat transfer class, so like the solutions here are probably not going to help you for this class, but yeah, just in terms of the formatting, that's what that's there for. And then there's a copy of the syllabus. So if I mention something and you want to double check it, or if there's any, if you want to look at the syllabus, that's there too. So that's all of like the introductory about the course, about the syllabus stuff. If there's no questions from there, then we can get into our first lesson. So like I was saying, this whole class is about understanding how and why nuclear reactors work and how and why they do what they do, as well as how to design them so that we are producing power, not harming other people and not harming the environment. So to do that, we're going to need a lot of knowledge that we're going to be developing in this class. To build a nuclear reactor, we first have to understand neutrons. We have to understand what they do when they move around in a reactor. So we need to understand what neutrons do when they interact with other nuclei. When a neutron interacts with a nucleus, we need to know what kind of reactions are going to happen. If we want our reactor to not like just keep producing neutrons uncontrollably, we need to have some materials that are like going to absorb some of our neutrons. So we have to design our reactors in a careful way so that our neutron population is steady. We're going to have to, for a given geometry, for a given system, know what the neutrons are doing. So how they're distributing themselves in terms of space, in terms of energy, in terms of time. And the most complete description would also include which direction they're moving. Although in this class, we can kind of, that's what the omega hat is. But in this class, we can mostly ignore the angular stuff. With that information, we'll be able to compute what kinds of production and loss rates we have for neutrons in our reactor. With all of that information, we can start putting this stuff together and design critical reactors. And once we know how to design a critical reactor, we can then set up the external systems that can take the heat that our reactor is producing and produce power. So like in our power plant that's shown here, heat's being produced in the core. You have coolant, water, which is both serving as a working fluid and as a way to maintain temperature. So the the water removes heat from your reactor, the water turns into steam and boils, that steam turns a turbine and produces power. So all of that is very fun and very cool when it works right. If you've got like a standard 1000 megawatt electric power plant, that's going to be producing the power for like 400,000 homes. So nuclear power is really cool. We can produce a lot of energy in a very, confined space. I think nuclear power is really awesome because it doesn't cause the problems that we have with fossil fuels. It doesn't cause carbon emissions, or to the extent that there are emissions associated with it, they're basically negligible. So in terms of things like addressing climate change, I think nuclear is a really important piece of that. So we want to know how this works. We also want to make sure that we're not doing it wrong, because we know that these kind of reactors can go wrong, and when they go wrong, they're pretty bad. Does anybody know what kind of reactor that is? It's got, sorry? It's got graphite. So usually our PWRs don't have graphite. Um, well, actually, I'm pretty sure that this is the RBMK. I believe that they actually are pressurized as well. But yeah, this was the Chernobyl reactor that blew up. Right. So we want to be able to know how to make sure that doesn't happen. And that's what hopefully we'll be able to see in this course. Just like a brief historical detour, because I think it's also important as scientists, as engineers, that we know the field, and that also means knowing like kind of how we got here. I'm not going to quiz you on history, but I think it's good to know that, and I think it's really interesting just to consider that like this this is a very condensed history. But the early nuclear discovery goes from like 1896 when we discovered radioactivity to 1945 when we did the first nuclear weapons tests. So like in less than 50 years, we went from understanding that radioactivity is a thing to making a nuclear weapon. That is like a pretty impressive span of time. And then so like the way that this started was just understanding, finding out that things can be radioactive, and Becquerel was studying fluorescence. Basically, before Becquerel, they thought that this phenomena of fluorescence was caused when like this because of the sun hitting some like piece of metal and making it fluoresce. So he was like doing these experiments to see with like printing paper. He was seeing the fluorescing patterns that were left on the paper, and what he discovered, there was a rainy day, so he couldn't do his experiment. So he had some uranium like rocks in this paper, and he put it in a drawer. He figured he wasn't going to be able to do the experiment. And then the next day when it was sunny, he went to pull it out, and he saw that the paper had the fluorescing marks on it that he would have seen if he put it in the sun. And that was when he realized that the source of these marks weren't coming from the sun, but were coming from the rock itself. So that's like the early discovery of like how we figured out radioactivity. Once we discovered that these materials are spontaneously emitting these particles, it was like, okay, let's see what happens when these particles hit other things. And that's basically the story of discovery of the electron, discovery of the proton, and the discovery of the neutron. We were just blasting these particles into other particles and seeing what came out of it. And so along the way, Mary and Curie discovered new elements. They were basically taking uranium pitch blende, which is like a uranium ore. They were separating it out into components, and then they found these new elements. So Mary and Curie were French, and this PhD is all about like basically doing reprocessing. So like historically, because that is where the French started, it kind of makes sense why the French lead the way in terms of reprocessing. So that's just an interesting thing to understand about like kind of how the field has evolved. 1905, Einstein discovers and publishes his paper about mass energy equivalence. When Einstein published this paper, they still didn't think that nuclear weapons were possible because nobody knew about the neutron yet. And if your only particle for interacting with the nucleus is like an alpha particle, is something that's charged, It's not going to be able to get into the nucleus. It's not going to be able to make it split. But once we discovered the neutron, we had this neutral particle that could very easily get into a charged nucleus. And then that opened the way for things like fission. And once we discovered the neutron and once we discovered fission, the race was on to make a bomb. And the discovery of fission was in 38. Does anybody know what happened in 1939? World War II started, right? Hitler invaded Poland in 1939. So like that's part of the reason why like the Oppenheimer movie is so interesting and compelling. It's like all of this science was happening at the same time that the World War II was starting, and it was a race to build the bomb before the Nazis did. And it's also a very interesting thing that in terms of like in the US, we built the first sustaining nuclear chain reaction. And Enrico Fermi was the scientist who was like mostly responsible for that experiment with Chicago Pile 1. Enrico Fermi was not an American. He was an Italian, and he came to the United States from Italy, escaping fascism. He was a scientist doing his science thing, and he would not do the Nazi salute. And he was forced to leave Italy. And in leaving Italy, he came to the United States. He helped do the Manhattan Project. He helped us make the bomb. So I think that is also very interesting historical information, just in terms of like the dynamics of history and how these actions unfolded ended up being very, very, very important, and I think ultimately good for the history. Um, so we discovered fission in 1938. In 1942, we had a self-sustaining nuclear reactor. 3 years after fission was discovered, we built a reactor, and we understood in that experiment, we basically understood a lot of the fundamental stuff about neutronics that we're going to talk about in this class. If you're interested in the history, if you look at chapter 2 of Adam's notes, it's the detailed story of the first pile, which goes into a lot of this stuff more. So I think these folks are kind of like they're like our educational grandmas and grandpas. They came before us, they did all of this stuff, and we are, kind of following in their footsteps. So yeah, that's just a little bit of the history that I think is good to know. And like ultimately, what we're trying to do to start this is just understand neutrons, understand how they interact with matter. So that was like the first thing I wanted us to get into in terms of like getting into the class. So the first thing that we want to consider, right? A lot of those first early discoveries, it was we're taking materials that are emitting these particles, we're shooting them into other materials, and we're seeing what happens. So this is kind of like an investigation of what that might look like, so this is showing you've got a monoenergetic, monodirectional beam of neutrons hitting a target that is thin and cold. And this target is made up of just one nuclide. And we're going to define some quantities here. We're going to use the symbol I. We're going to use the symbol I to represent the beam intensity. So that's the rate per unit area that neutrons are hitting the target. So in terms of the units of the intensity, it's going to have units of neutrons per centimeter squared per second. So it's a rate, it's neutrons per second, but it's also per unit area. This material is made of atoms. There's going to be an atom density, and we're going to use the symbol capital N for the atom density. And so the units of that are going to be Okay, it looks like it is still recording, which is nice. Sorry about that. Okay. Um, so this product IA, oops. What we were saying is we can think of that as like the crossing rate. So it's the number per unit time that are hitting our materials. Um, and it's also going to depend on the numbers of particles that are there per unit area. So that is going to be the product of N and delta X, right? Because N is the atoms per volume. And if we take that atoms per volume and multiply by that thickness, that's going to give us atoms per area. So we can think of that product as like the areal density. So the areal density means atoms per centimeter squared. It's a density in terms of the area. Um, so those four things is what the collision rate is going to depend on. And if the collision rate depends on all of these quantities, then we can turn this this little alpha symbol means it's proportional to. So if we know that the collision rate is proportional to all of these things, then we can turn this into an equation that just includes a proportionality constant up front. And that proportionality constant we call little sigma total. So that is our proportionality constant. And then we have all of these other terms in our equation, IA and N times delta X. So let's just make sure that the units make sense based on all the quantities that we've defined here. So we're saying that this collision rate is going to have units of particles per second. And if this is an equation, then the units on each side should match up, right? So we're still maybe unsure about what the units of the sigma t are, but we know about the units of those other two terms, right? We already said that IA was the crossing rate, so that has units of neutrons per second. And what I'm showing in the brackets here, that's just the units associated with each term. So that's the units associated with I times A, and then the units associated with N times delta X. We said that that's like an areal density. So it's like atoms per centimeter squared. And so based on the dimensions that we have in this equation, we can kind of figure out what the units of sigma t has to be so that we have the units on both sides matching up, right? So if we want to have particles per second or neutrons per second on the right-hand side, what do the units of sigma t have to be so that the units on each side are balanced? If we want to have particles per second on the left, what units does sigma t have to be so that the units match up? Yeah.
Oh, it's not particles and it's not
Yeah, the neutrons are the particles here. Yes. Yeah, they have the same units. I and A basically have the same units. So that means that sigma t has to have the reciprocal units of N times delta X, right? That if sigma t were to have units of centimeters squared per atom, then we could see that the units kind of cancel, that the atoms, oops, sorry, the atoms don't cancel. We can see that the centimeters squared cancel the centimeters squared, sorry, and the atoms do cancel the atoms. So in that sense, we are left with neutrons per second or particles per second. I guess just in terms of making all these units look right, I'm going to erase particles and just call that neutrons so that there's not any confusion in terms of what the particles are. But yes, so this sigma t, this proportionality constant ends up, what we just showed is that this quantity sigma t, this is what we call, we give this quantity a name. We call this the microscopic cross-section. And technically it's the microscopic total cross-section. So that's like the first nuclear engineering term that we are going to define today, the microscopic total cross-section. This is like the proportionality constant that tells us about how many, it basically gives us, like, if we just think about the units of this term, right? It has units of centimeters squared per atom. So that that proportionality constant has those units, right? It has units that what we just saw, the units of this term are centimeters squared per atom, or we can say area per nucleus. So that's a very compelling and kind of nice definition, right? That this little proportionality constant is just representing the area of that nucleus. And that is not the exact, that's not a, that definition is useful in terms of understanding kind of what's going on, but we do want to keep in mind that these neutron nucleus interactions, we're talking about these particles. So really, this is like a quantum mechanical phenomena. So like it's not exactly the area because some nuclei can have cross sections that are like way more, many more times the actual area of the nucleus. But it is still helpful to think about it as an area per nucleus. And the kind of the extension to that is that we can think of it as basically the effective area. We can think of this cross section as the effective cross-sectional area that the neutron presents to the nucleus. That the neutron, sorry, that the nucleus, I have that backwards. It's the area that the nucleus presents to the neutron. That the nucleus presents to the neutron. So that's the definition that I want us to have for the microscopic cross-section. We want to think of it as kind of like an area, but we want to have the knowledge that it's not actually an area. Do we know the units that are common for the microscopic cross-section? It's got a, sorry? So it's centimeters squared, but in nuclear engineering, we give that a special name because yeah, barns, right? So these are, if you look up a macroscopic cross-section, the units are going to be in barns. They use a symbol little b for that. And one barn is defined as 10 to the negative 24 centimeters squared. So yeah, very small areas when we're talking about the area of a nucleus. And yeah, if you look up tables or if you go onto like Janus or any nuclear data situation, that's the units that they're going to associate with that cross section. And this cross section depends on two things. We know that, for example, if we're talking about like a fission cross section, that it's going to be different for uranium than it is for, say, carbon, right? So it depends on the type of nucleus. Different nuclei are going to have different cross sections. So if we have a material that we want to put in our reactor, we want to know what its cross sections are. And then it also is going to depend on the relative, this is based on a collision. So it's actually going to depend on the relative speed between the neutron and the nucleus. So we can say the relative speed between the neutron and the nucleus. That was why we mentioned in the first problem that it was a cold target. It means that we can assume that those atoms are not moving very much. And ultimately, that's an assumption that we're going to want to try to make, or at least an assumption along those lines is what we're going to try to make so that when we have a microscopic cross-section, we can kind of ignore some of these functional dependencies. So before we get into the kind of that part of the discussion, I just wanted to talk about a little bit more about how we think of and what makes up the total cross section. Because when a neutron interacts with the nucleus, there's kind of two main possible avenues for what that reaction can be. If a neutron interacts with the nucleus, we can basically either be absorbed or we can scatter. So the sigma, the total cross section is going to be the sum of both the absorption cross section and the scattering cross section. So those are basically the only two options for a neutron to interact with something. It's either absorbed into that material or it scatters off the material if they interact. And when we think about absorption, when a neutron is absorbed, there's a lot of different possible things that can come from that absorption. Can y'all think of any absorption reactions that might make up the total absorption cross section? Yeah, so you can basically have, we'll say that sigma, you basically have a photon come in and a neutron come out, right? So you can say gamma n. Any other kinds of absorption reactions that we can think of? Fission, right? That's like our favorite one, sigma F for fission. When a neutron is absorbed, it might not cause a fission, it might just the nucleus might just get excited and then spit out a photon. That would be radiative capture. So we can say plus sigma C, or sometimes people also use sigma gamma for radiative capture. And I'm just going to put dot 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 because there are a lot of there's N2N, there's N3N, there's N4N, there's N alpha. There's a lot of possible reactions that we could have. But for the most part, fission and capture are like the main ones that we consider, but there are a lot of reactions. So in your specific application, you want to just be aware of if like N2N for my nuclide is a dominant possible reaction. I just want to be aware of that when I'm doing my calculations. And then in terms of the different kinds of scattering reactions, are we familiar with any kinds of different types of scattering? Yeah, right. So we could say sigma E for elastic. If it's elastic, the other option could be inelastic, right? So I could say sigma N for inelastic. There's other scattering reactions that yeah. Oh,
For scattering, saying, or
yeah, we're saying that the scattering could be elastic, it could be inelastic. We're kind of differentiating those two.
okay. So that's like more broad.
Let's see, Compton scattering. Compton scattering is when neutron comes in and neutron bounces out, but also photon comes out? Or right. So I think that, I guess my initial inclination is that that's kind of like it's that's a good question. I don't know exactly how I would categorize that. I don't know if I would categorize that as a type of scattering reaction or as a type of absorption that ends up like, I don't know if it's a compound nucleus that's formed. I don't remember if it's a compound. If it's a compound nucleus that's forming, then we would call that like a radiative capture, versus if it's not forming a compound nucleus, it would be more of like a kind of scattering. I just don't remember which one is which. But then in terms of these other scattering reactions, we could have potential scattering, where the neutron just scatters off the nuclear potential. And again, there are, just like there's a lot of absorption reactions, there's a lot of scattering reactions too. And normally we don't really pay attention to all of them. But it's good to be aware that there are a lot of different reactions that we can have. And depending on our nuclide, some kinds of reactions might be more important than others. So if we think of sigma total as being the sum of these two reactions, which is also the sum of all of the sub-reactions that absorption can be and that scattering could be, then we can think of the ratio of any type of reaction over the total as like a fraction, where any reaction, all of the reactions in total give us the total, and sub-reaction, if we do the sigma x divided by the sigma t, it's giving us like a fraction or a probability that that one type of reaction is occurring. So that's one of the most important things about these cross sections, is that you can take ratios of them to figure out what kinds of reactions are more likely. So this ratio gives you the probability of a type X reaction. And that sigma X could be any kind of reaction. It could be fission, could be capture, could be absorption. And yeah, so that is a very common kind of question. It's also a useful thing to know when you're trying to categorize a material, what it's likely to do. These probabilities can be helpful. So that's just the general straightforward definitions for how we think about what makes up the total cross section, and also that we can think of the cross section as being related to probabilities. So this table just kind of summarizes all of that stuff. Again, these are non-exhaustive, and this also spells out in words what all of those cross sections mean. In general, if the nuclear structure changes in a reaction, then it is an absorption reaction. And if the nuclear structure doesn't change, then it's just a scattering reaction. So this is a plot of the microscopic cross-section for uranium-235. This is showing that the microscopic cross-section is a function of energy. It's a function of the incident neutron energy. So some like things to notice from the plot is that at any energy, the red curve is the sigma for fission and the blue curve is the sigma for capture. So for all energies, the sigma fission is larger than the sigma for capture. When we are in the thermal energy range, so when our energy is like less than, I don't know, 10 to the -1 eV, then sigma F is basically the dominant reaction. Like if you look at sigma F and sigma T, they're basically right on top of each other. So it means that at a low energy, if U-235 absorbs a neutron, the most likely thing to happen is going to be a fission reaction. And the other thing that we can see from this plot is that in these ranges, in the low energy range, the plot for this is basically linear. And so what we can say is that this cross section follows 1/V at low energies. E sub n is the energy of the neutron. So just like we were talking about before, if you do the ratio of two cross sections, that gives you a probability of a certain reaction occurring. So if for this plot, anywhere on this plot, if we were going to do sigma F divided by sigma capture, sigma F is larger than sigma capture. So that ratio is going to be positive. That means that if a neutron is absorbed, it's much more likely that it's a fission than a capture. So at low energies, when uranium-235 absorbs a neutron, the most likely interaction is going to be fission. And depending on the neutron speed, that's going to give you a corresponding neutron energy. In the low energy range, we can mostly assume that it's a classical expression for the kinetic energy. And so if we talk about the neutrons being in thermal equilibrium with their surroundings, that is usually where the thermal energy range is defined. And I have one of the homework problems is going to have y'all investigate, basically do the calculations for if I'm at room temperature, if my reactor is at room temperature, what speed should the neutrons be moving? So that's kind of where those numbers will come from. So the next thing to talk about is the macroscopic cross-section. And if we go back to that the collision in our cold target, what we would see is that our microscopic cross-section and the big and the atom density appear next to each other in the equation. And that product is what we call the macroscopic cross-section. So in that equation, the number density times the microscopic cross-section gives us the macroscopic cross-section. So we already said that big N has units of atoms per unit volume, atoms per centimeter cubed. And then we said that the microscopic cross-section has units of centimeters squared, or area per nucleus, or area per atom. So what does that mean that the units have to be for the macroscopic cross-section? Yeah, it has to be 1/centimeters, right? We can see that the atoms are going to cancel. The centimeters squared up top will cancel 2 centimeters down here. So the macroscopic cross-section is going to have units of inverse centimeters. So in terms of like a physical meaning for those inverse centimeters, it's basically telling you how many reactions your neutron will have per unit distance traveled in the material. So that's what the meaning of these inverse centimeters are. It's telling you the expected number of reactions. Expected number of reactions per distance per neutron distance traveled. Um, so oh, there's a quantity in here, capital N. Are y'all familiar with, like, if I gave you a material, like if I said iron, do y'all know how you would calculate the atom density of iron? Just like thinking about a general formula for big N. And if not, it's okay. It's a very so if you take the atoms, if you take the mass density, and if you take Avogadro's number, and then if you divide by the molar mass, that's the general formula for the atom density. And we can just spell out all these terms. Rho is the mass density. And so that has units of like kilograms per centimeter cubed, right? It's a density in terms of the mass. N sub A, that's Avogadro's number. So that's like the 6.022 times 10 to the 20, oh no, the 10 to the 23rd or 20 to the 23rd? I think it's 10 to the 23rd, and that's atoms per mole, or atoms or particles per mole. And then big M, oh, sorry, so that's the units. And then big M, that's the molar mass. So that's, or the atomic mass, that's the mass that you would see on the periodic table. So that has units of grams per mole. And I guess just in terms of making my units nice, I'm gonna take back what I said about mass density and just say it's grams per centimeter cubed. So that hopefully what you could see, if you plug those units in to this equation, your resulting formulation for N comes out in units of atoms per unit mole. So if we were unaware of that one, that's okay, but that is one that we want to know. Because I might give you a material and I might say, iron has this mass, it's iron 54, so you would know what M is. And then with that information, you can calculate the atom density, and then you could calculate, say, macroscopic cross-section if I also gave you the microscopic. So that's the definitions we want to have for macroscopic cross-section. And it is also going to depend on, basically, notice that the macroscopic cross-section is N times the micro cross-section. So it depends on the same things that the microscopic cross-section depends on, right? It's also going to depend on composition. And it's going to depend on VREL, the relative velocity between the neutron and nucleus. Right? Depends on those same things, but then it also depends on anything that the atom density depends on. So that means it also depends on the mass density. Oops, sorry. And the density of a material will also depend on its temperature, right? Because if you heat something up, the density will decrease. So the last thing that it depends on is temperature.
What's number three again?
2 is the relative, so that VREL is the relative velocity between the neutron and the nucleus. So the first 2 is the same dependence as the microscopic cross-section because it's in the equation. And then the 3 and 4 are what the atom density depends on. So with all of that being said about the macroscopic cross-section, we can kind of extend, or really it's generalizing what we did for the cold target with one nucleide to say, in our real problem, we're probably not just going to have one nucleide. We might have a mixture of nucleides. So how do we compute a cross-section if we have a mixture? So what we're going to imagine is basically the same picture that we had in the cold target, but now there's 2 different atoms in our material. So what we can think about is what would the collision rate be with just one type of nucleide? So like if we wanted to say what's the collision rate with just our nucleides that are type Y, then it's going to be the exact same collision rate formula, but we're going to use the cross-section for type Y atoms. So like using our collision rate definition, it's going to be the intensity I times the area A times the target thickness delta X, and then times the macroscopic total cross-section for atom of type Y. So that's what this last term is. It's total cross-section, and then the superscript is saying for atom of type Y. And we just talked about how we can define the macroscopic cross-section in terms of the atom density and the micro cross-section. So that's what we can rewrite this expression using that definition, that this is also the same thing as I times A times delta X times the number density of Y times the microscopic total cross-section for atom Y, right? All I'm doing there is just rewriting this in terms of its definition. It's just the atoms that are type Y. And basically what we're saying here is that when these neutrons come in, they're either going to collide with a type Y nucleus or a type Z nucleus. And so if this is the expression for type Y, what would the expression for type Z look like? Perfect. Yeah, exactly. It's just going to be the exact same definition, but just with a type Z nucleus. So that means that in our macroscopic cross-section, we're going to have a superscript Z for type Z. And then when we, recast in terms of micro and atom density, we'll also use that same superscript. In this case, it's more simple than that. And it's just what are so like if your fuel was uranium dioxide, so it contained uranium and oxygen, that would be more like one. Yeah. So yeah, this would be N times Z times times the microscopic cross-section total for type Z. And the interesting thing about if you consider the beams coming in, it can either hit one or the other. If a beam hits a Y nucleide, does that affect what happens with the Z nucleide? Like when these neutrons are coming in, does the interaction with one nucleus interfere with the interaction of another? So like I guess imagining that same picture of the beam coming in. What we want to hopefully recognize is that, like, say our beam comes in and it hits this guy. If our beam comes in and it hits this type Y nucleus, that has no effect on if another neutron comes in and hits this type Z nucleus, right? So these interaction rates don't interfere with each other. They do not interfere with each other. So that's nice. And part of the simplifying assumption here is that we're assuming that it's a cold and it's a thin target. So there's not like there's not multiple layers of atoms, it's like one layer. So if it hits one, there's nothing behind it to like shield it from the back. So in this case, the total collision rate then is just a question.
Sorry. It's like, oh, the actual temperature wise or energy?
Technically it's both. And that if the target is cold, it means it's kind of like a simplified like 0 Kelvin, no thermal, no intermolecular or like no vibration. And that means if it's not vibrating, it also would have 0 temperature. Yeah. So yeah, that's a simplifying assumption. But yeah, so what we're saying is that the collision rate is the sum of the y and z rates. And then that means that if we want a collision rate for the whole mixture, all we have to do is add up those two expressions. And the I is the same, the A is the same, and the delta X is the same. And when we add the sigma Ty and the sigma Tz, that's just going to give us a sigma total for the mixture. And what we're saying is that that sigma total for the mixture is just the sigma totals of the individual components. So that's just the sigma total for Y, sorry, sigma total for Z plus the sigma total for type Y. Right? So that is actually very nice and convenient. It means that if we have multiple nuclides in our target and we want the total cross section, we just compute the cross sections for the individual components and then we add them up to get the total for the mixture. So in terms of a general definition, sigma total for a mixture is just so I could write summation like with the big sigma, but then I'm also going to have macroscopic cross section in there too. So I'm just going to say sum I equals 1 to n. Sorry, I equals 1 to little n of sigma t I. Hopefully that's clear. I didn't want to use two summation symbols because then I'm going to have a big sigma and then another big sigma, and it's going to look weird. But hopefully that's clear. That's how you would handle a mixture. And now that we have that, I think that's most of the kind of that's most of what we need to know about just the kind of basic definitions for cross sections. And now that we have that understanding about cross sections, we can get into more about understanding what happens to the neutrons as they were to go into a material that is not a thin target, but a material that's like arbitrary, has an arbitrary thickness. So we're going to have a similar picture that neutrons with intensity I are coming in, and we want to look at in this material at some arbitrary location X. We want to look at what's the intensity at this location, and then we want to say, if I go some small distance delta X to the right of there, what's the new intensity and how is my intensity change? So if this is X plus delta X, if I look in that tiny little interval from X to X plus delta X, it's almost like I'm looking at a thin target, right? Because delta X is very small. So what we want to do is in this little interval, we want to apply a principle of conservation. And general conservation, the way that we can express it is that the rate of change of some quantity, so we'll say the rate of change of some quantity that we'll call Q, where Q could be any quantity. It could be some kind of amount, like the number of neutrons. It could be a density, like the neutron density. We're looking at the rate of change of some amount. And generally, if you're applying conservation, the rate of change of a quantity is going to be the rates of gains of that quantity minus the rates of losses of that quantity. So we can say gain rates of Q minus the loss rates of Q. And you might have multiple gain rates or multiple loss rates. Any gains would be positive in that equation, and any losses would be negative. So that is like a very important, it looks simple, but there's so much packed into that equation. And that's actually like kind of going to be our starting point for when we're deriving neutron distributions. We're basically always going to start with this principle of general conservation. We're going to look at for our specific problem, how we're, in this case, we're going to be balancing neutrons. So we're going to ask, how are neutrons being produced? How are we gaining neutrons in our system? How are we losing neutrons in our system? That requires that we understand our production and our loss rates. And once we can express all of that mathematically, then we can start designing reactors that are critical and doing all the fun stuff that we want to do. So that equation right there is going to carry us a long way in the course. And we can also apply it here to the intensity of our neutron beam. And we can ask, what's the change in intensity in this problem? And then what are the gains and what are the losses? So in this case, the change in intensity is saying, how much is my function changing as I go through this little piece of my as I go through this material. So I is the value of the intensity, and the change would be the intensity at x plus delta x minus the intensity at x. Right? Change in intensity is just like final minus initial. So the value at x plus delta x minus the value at x. If neutrons are going into this material and it's not a fissioning material, is there any way that the intensity can go up? Is there any gain mechanisms if there's no like fission in the medium?
That's possible. Is that they can still.
Well, I'm asking if there is no fission, do we have any gain mechanisms? The moderator would slow the neutrons that are there, but it wouldn't increase the number, right? Yeah. So if we think of the intensity as the neutrons per unit area and per unit time, even if there was scattering, it wouldn't change the number of neutrons. Like the neutron would just come in and it would hit something and it would move off in a different direction. So the population wouldn't change in a scattering reaction. And so if there's no way for neutrons, if there's no fission in the medium, and there's no neutron sources, then there's no way that we can be adding neutrons. Then there's no way that we can be adding intensity. So there's no gains if there's no fission or ways that neutrons are being produced. But there are going to be losses because as neutrons collide with particles in this little medium, they have now collided. And so I guess technically, actually, I'm rethinking how I've defined uncollided. And so technically, going back to your question about scattering, technically that would remove a neutron from the uncollided beam. But that would be part of the total cross section, right? So like any absorption would take the neutron away because it would be absorbed. Any scattering would be part of the total, and that would mean that the neutron had an interaction, so it would be removed from what we would call the uncollided beam. So just thinking more carefully about your question, the losses of intensity is actually due to any kind of collision. So that losses of intensity is actually just the collision rate that we derived in the previous slide for the thin target, but just divided by area to make it an intensity. So the collision rate, the loss of intensity is due to the collision rate. So it would just be sigma total times our intensity at that specific value of x, and then times the thickness. This is just our collision rate definition, but we've divided the area out to go from a collision rate to an intensity. So we use conservation to set up this equation. And the next thing that we want to do, what we're going to do is just divide both sides by delta x. So if I divide by delta x and I divide by delta x, then those delta x's cancel. And then on the left side, I have the intensity at x plus delta x minus the intensity at x, all divided by some delta x. And this expression on the left-hand side hopefully looks similar to the derivative, or at least the derivative before you take the limit. And what we're saying is that in this little interval, delta x is very small. So if we take this expression and then take the limit as delta x goes to 0, we take this whole expression and we take the limit as delta x goes to 0, then what we have on the left is the limit definition of the derivative, right? That, and so what we can then say, and I guess I'll show it here, that means that the left side is di dx. And what we have on the left, notice there's no delta x on the right side. So when we take the limit, we've already divided away the delta x. So the right-hand side doesn't change. This is negative sigma t times the intensity at x. So we've taken our conservation equation and we've derived, or we've come up with a differential equation for the intensity of our beam. And this is a differential equation that we can solve. So that's what we will do. Oops. That's what we'll do next. And so just kind of jumping back to basically where we're at is that we have di dx is negative sigma t times I of x. And we have an initial condition, which is that the intensity at x equals 0 is this initial intensity I naught. And so this is a differential equation. We can talk about the type of differential equation. This is a, so when we talk about differential equations and categorizing them, one of the things that we can talk about is the equation linear or is it nonlinear? When y'all look at an equation like this, can y'all tell me if it's linear or nonlinear? So linearity is based on any powers on the function that you're solving for. So in this case, the function that we're solving for is I. What's the highest power on I in our equation? 1. So that means that it's linear, or yeah, that means that it's a linear. The highest power on our variable is, and then we can talk about the order, which is about the highest derivative that appears. So what's the highest, do we have any second derivatives? We only have a first derivative, right? So that means that it's a first order. And this is an ordinary differential equation because the intensity only depends on x. It doesn't depend on multiple variables, in which case this would be a partial. Like if the intensity depended on x and t, then it would be partial differential equation, but it's just an ordinary one. And this equation is really nice because we can separate it. We can get anything that depends on I on one side and anything that depends on x on another side, and then we can integrate each side. So like, for example, I of x and di, we want those on the same side. So if I divide both sides by I of x, then I get 1 over I of x di. And I'm also going to multiply both sides by dx. So that means that on the left-hand side, I have negative sigma t times dx. I'm treating di dx as a fraction. I'm moving the x part to the right side, and I'm taking the I that's on the right and I'm moving it to the left. So now everything on the left-hand side depends on I. Everything on the right-hand side is either constant or depends on x. So I can take this equation and I can integrate both sides. So on the left-hand side, I'm integrating 1 over I with respect to I. What should that give me? Yeah, natural log, right? So we can say that this is ln of, technically, if we want to be correct, we'll say absolute value of I of x, but The intensity is always going to be positive, so that kind of doesn't really matter. And then what's the integral of a constant with respect to x? It's just going to pick up an x, right? So this is going to be negative sigma t times x. And then I didn't add any bounds on my integrals, so I also need to add an integration constant like a plus c. Yes, sir. And so now, if I want to find the c, I need to apply my initial condition, but I also probably want to get that natural log out of there because I don't like natural log in my equation. How would I clear the natural log? Yeah, exponentiate both sides, right? So if I do e to this power and then e to this power, the e and the natural log kind of cancel, right? So I get I of x. And then I have e raised to a power where I have two things being added together. So e to the a plus b is e to the a times e to the b. So this is the same thing as e to the c times e to the negative sigma t x. Just properties of exponents. And now that equation is in a really nice form where I can apply my initial condition. So if I apply that initial condition, we know that I at x equals 0, I can evaluate this equation at 0. E to the 0 is going to give me what? When I plug in x equals 0, it's going to give me a 1, right? So this is just going to look like e to the c. And I know the intensity at x equals 0 is this value I naught. So that means e to the c is that constant I naught. Therefore, my final answer looks like this. I of x equals I naught times e to the negative sigma t times x. So, whoa, sorry about that. So what this is telling us is that as neutrons pass through this material, they get attenuated, and they get attenuated in an exponential manner, right? E to the negative sigma tx means as I plug in values of x, the initial intensity is decreasing in an exponential way. So we say that uncollided neutrons are exponentially attenuated. So that hopefully agrees with what we've seen in our previous courses with like charged particles versus neutral particles. The neutral particles will be exponentially attenuated, so they'll follow some kind of trend that looks like that. Any questions in terms of how we set this equation up, how we got our final answer? Yes.
Like defer to just it's the way where we find it by the cross section.
So the attenuation coefficient is the same thing as this sigma t, but for photons. But the equation would actually be the same. It's just that if you like were doing photon attenuation, you would be looking in a different place, like the NIST tables or whatever, versus, yeah, for this, you'd be looking at like a cross-section place. But yeah, the governing equations are the same. Yeah, it's just a different type of attenuation coefficient. Alrighty. So the next thing, and like a very kind of similar thing, we've got neutrons passing through this medium. We're saying they're exponentially attenuated, but we might also want to know about like how far do they go before they just interact in the first place? And that question, or that quantity, how far do they go before they collide? We give that a name and we call that the mean free path. So the mean free path, that's just how far on average does my neutron go before it has a collision. And so the way that we can set this up is we can think about what is the probability that we have a collision in some interval divided by how many neutrons were coming in the first place. So the probability that we have a collision in that first interval, that's just the intensity expression that we had in our differential equation. it's just going to be I of x times sigma t times the thickness in that interval, which is going to be dx. And then that's all divided by the initial intensity, which was just I naught. And then when we're moving through the material, we now know what I of x is, right? We just came up with that expression for I of x, that I of x is I naught times e to the negative sigma t x. And then we still have our sigma t and our dx all over I naught. So notice, oops, notice that we have an I naught on the top and on the bottom. So those are going to cancel. And then this expression for this probability is going to look like just what I have in the numerator. It's going to look like sigma t times e to the negative sigma t x times that differential thickness dx. So this is the probability density function for the neutrons that are in our beam, and it tells us at a certain value of x, what's like the probability that our neutron is still alive, right? So like if we plug in x equals 0 into that equation, e to the 0 just gives us like a 1. So you can almost think of that as telling us that at x equals 0, no particles have been lost from our beam. And then as you plug in larger values of x, that e to the negative quantity is going to make it smaller and smaller. And if you were to plug in x equals infinity, then e to the negative infinity would go to 0. So it's like at x equals 0, our probability is like 100%. And then as x goes to infinity, our probability goes to 0. So this is a probability density function, and we can use it to compute the mean free path. We just need to know the definition of an average, and that's just kind of like a calculus definition. So the average value of some function on an interval is the integral over that interval. So like if the interval is x1 to x2, then we integrate the function that we are trying to find the average of times some weighting function with respect to x. That's what the numerator of our expression looks like. And then the denominator is just integrating the weight function. So we're integrating over the same interval, so x1 to x2 of our weight function with respect to x. And this wx is just, it basically is going to be a probability density function. It has to be a function that is 0 somewhere and eventually is always positive and has a 0 somewhere. So that wx meets the criteria of this p of x. In other words, wx is actually our probability density function. And then we can use this definition. And then we can use that definition to compute or come up with an expression for the mean free path. So with the mean free path, x is the quantity, x is the function whose average value we are trying to find. So x has been replaced, f has been replaced with x, and then w is the probability density function. So I'm putting that. And in the bottom, notice that in the bottom here, we're integrating a probability density function over its whole domain. So what is that going to be equal to by definition? Yeah, that whole denominator is equal to 1 just by definition of it's a probability density function. The integral of a probability density function over the whole domain is 1. So that simplifies the denominator, and then our numerator is integrating 0 to infinity of x times that p of x, which what we saw previously is that p of x is sigma t times e to the negative sigma t x, and then we have a dx in there as well. So this integral is what will give us the mean free path. Is there anything that we can do to simplify this integral? Yeah, sigma t is a constant, right? So we could pull that up front. That's a good thing to do. And then inside we've got x times e to the negative sigma t x dx. So what I will say is that this integral right here can be done by integration by parts. I think it would be a good exercise. In the sake of time, I'm not going to go through it because we're running short on time. That is not a bad integral to do. If you, I think it would be a good exercise to just prove to yourself that you can work that integral out. And ultimately, what you're going to end up showing, if everything goes well, is that the mean free path, x bar is the symbol that we use for the mean free path. And ultimately, this whole expression on the right-hand side is going to work out to 1 over sigma t. So I will leave that as an exercise for y'all. But that is the definition that we can use for the mean free path. And notice that it means that our mean free path is inversely proportional to our cross section. So the larger the cross section, the smaller our mean free path is going to be, which kind of makes sense that if sigma t is the distance traveled per collision, if that value is larger, then the mean free path is going to be smaller. It means you're having more collisions every distance that you travel. And so for individual reactions, we can also define our own mean free paths. The absorption mean free path is just 1 over sigma A, and the scattering mean free path is just 1 over sigma S. So if I want to know like how far does my neutron go before it's absorbed, how far does it go before it's scattered, that's what those quantities could tell me about. So that's our mean free path. The next thing I wanted to do was talk a little bit about temperature dependence and some of like the complicated part of the microscopic cross section is that it depends on the relative speed between the neutron and the nucleus. But if it didn't have that dependence, our reactors would actually be less safe. So that dependence complicates things, but it complicates things in a good way for us. And hopefully I can help us understand why that is. In any material, like in this desk, in this computer, it's made of atoms, and those atoms, even though we can't see it, they are vibrating in place. So it's the same thing in our nuclear reactor. All of the atoms in our reactor are vibrating, and we can make a simplifying assumption, which is that those vibrations are isotropic. That means that they're the same in every direction. And if that's the case, then all of these vibrating molecules, we can look at them as having a certain distribution that we call the Maxwellian distribution. So if all of our atoms are vibrating isotropically, then we can approximate them with this Maxwellian distribution. And this Maxwellian distribution, it's only a function of temperature. So that means if we assume that it's isotropic and we know the temperature of our medium, then we can use that information to approximate what the distribution would look like. And if we make the assumption that it is isotropic and that our nuclei are vibrating in this Maxwellian distribution, it allows us to simplify our dependence on the microscopic cross section. So like we initially said that microscopic cross section is going to depend on the relative speed between the neutron and the nucleus or the atom. So this is the speed of the neutron, or the velocity of the neutron, and this is the velocity of the atoms in the medium. So if we assume that our neutrons have an isotropic distribution, then we can take away the directional dependence on our neutron velocity. So this would make our cross-section just be a function now of the neutron speed and the velocity of the atoms. Absolute value here saying that we're going from a velocity to a speed. And if we also assume that our nuclei are in a Maxwellian distribution, then that allows us to replace the velocity of the atoms with just a temperature dependence. So this is just going to be now, I'll say Vn for the speed of the neutron and T for the temperature of the medium. So if we make these assumptions, the microscopic cross-section, now it only depends on the speed of the neutron and the temperature of the medium. Temperature is really easy. Speed of the neutron also, because speed and energy are 1-to-1, we can express this dependence on the speed of the neutron, but we can also just express it as the energy of the neutron, which ends up being a lot more convenient for us. So ultimately, we can now represent this as a function of the neutron energy and the temperature. So these assumptions are really important because it means that it makes our cross sections a lot more easy to look up and deal with. So anytime that we're given a cross section, those are usually the assumption. Like you guys have seen many problems where they just give you a value for like the fission cross section. If they're not explaining much about any of the details of that reaction, they're probably making these assumptions about how what its dependence is. And we will use these assumptions kind of extensively in this course. So whenever we look at a cross section, like a microscopic cross section, we'll see these little these peaks. This is the resonance region, and if we look at this resonance right here and we zoom in on it, what we would see is that the first peak, that's what that resonance looks like if we're at a certain temperature. T2 and T3 are at higher temperatures. So if we were to take this reactor and then we were to heat it up, what we would see is that these cross sections are actually going to, the peak is going to go down, but they are also going to be broadened. That's what this picture is showing, is the process of, or what Doppler broadening looks like. So anytime that the reactor temperature changes, specifically if the reactor temperature goes up, we're going to see this phenomena of Doppler broadening. This happens to our cross sections. And basically, if we look at this plot, at E0, which is like the neutron energy, when the temperature was low, we had kind of like a big peak. And if our energy was some range around there, this first peak, notice that like if we're at, say, these energy ranges, the probability associated with that original function becomes pretty small. And the probability associated with our second temperature function and our third temperature function is actually higher. So at the energy around the neutron energy, as the temperature increases, those cross sections broaden, and those cross sections broadening means that more neutrons of various energies can participate in these capture reactions. So you basically get, when the temperature goes up, these cross sections broaden, and it increases how much capture you have in your system. And if neutrons are being captured, it means that they are not able to cause a fission. So the fact that your reactor temperature has increased and these cross sections have broadened means that your reaction rate, specifically your fission rate, actually goes down. So increase in temperature ultimately makes the fission rate go down, and that's an example of negative feedback. And that's what we want in our reactor. We want negative feedback because it means that if there's some kind of perturbation that changes the state of our reactor, we want that perturbation to not make the reactor go into a dangerous configuration. That was the part of the problem with Chernobyl, is that it had a positive void coefficient. So positive reactivity coefficient meant that if the temperature go up, the reactivity could go up as well, and it causes big problems. So this is a good thing to know about. It gives us a way to it basically means that just by nature of the temperature dependence of materials, there's kind of a built-in negative feedback effect there. Let me see how much more I've got. Okay. So the next thing that we wanted to talk about is just what happens to neutrons that come out of fission. So if we consider just like the general fission reaction, there's a lot of different byproducts from this fission reaction. Some things that are going to come out of a fission reaction are fission fragments. Those are like the pieces. Oops, I can write better than that. Those are like the pieces of the nucleus that it splits into. In a fission reaction, we're going to get neutrons. In this process, we will also produce other particles that are not going to like help our chain reaction, but we want to know about them, like it's supposed to be neutrinos. And we also will get beta particles, and we will get gammas. We'll kind of get a lot of stuff from a fission reaction. Um, and some things that we should know about fission in general is that it is going to be dependent on, we know that the fission reactions depend on the neutron energy that caused the fission, but when neutrons are born from fission, they don't really care what the initial neutron energy was. So neutrons born from fission are independent of the incident neutron energy. They're independent of the incident neutron energy. So it means if the neutron is 1 eV that causes the fission or 1 MeV that causes the fission, the energy of the neutrons that come out of that process, it isn't going to really change. In terms of the neutrons that come out of fission, they don't have any preferred direction, so they are emitted isotropically. And so they don't have any preferred direction. They also don't have any preferred energy. The neutrons that come out of fission have a range of energies or a distribution of energies. So they have a energy distribution. And we give that energy distribution a name. We call it the fission spectrum. And we use the symbol chi of E for the fission spectrum. And its units are inverse energy. So the fission, and that's what this red plot is shown here. That's the fission spectrum for uranium-235. So it has the characteristics of a probability density function, which is that it's 0 somewhere, and it's always positive. If you look at the area under that curve from 0 to infinity, you better get 1 because it's a probability density function. And it has units of inverse electron volts. The other thing that's shown here is the cumulative distribution function, which you can get the CDF from the PDF. And what we can see on this fission spectrum is that there's a range of energies that neutrons come out with, but there's also a most probable energy, right? This distribution has a peak right here, which is around 1 MeV. So the neutrons that are coming out of fission have a most probable energy around 1 MeV. So when we're saying like, what's the fast range for neutrons? Usually we'll say it's around 1 MeV because that's where the most likely neutron energy is. So that's the fission spectrum. And yeah, it's a probability density function. So it's telling you the probability per unit energy that a neutron is born, probability per unit energy that a neutron of some energy causes the neutron to be born. So that's the fission spectrum. And so we've got these expressions for beam intensity. We're thinking about this dependence on energy. And in general, we've been making these assumptions about, or we want to think about what does it mean to make this assumption about the nuclei vibrating in this Maxwellian distribution. So we already have a collision rate expression, and we can just include that there is going to be some dependence on the energy of the neutrons in our cross sections. So the collision rate is the intensity times the total cross section, which is a function of energy. And then it's also times the area of the target and the thickness of the target. So that's just kind of returning to our general, oops, sorry, that is an area. That's just returning to our collision rate definition, including an energy argument on the macroscopic cross-section. Notice that in this expression, we also have the product of the area and the displacement, or the area and the thickness. So for like a square or like a brick-shaped target, the area times the thickness is going to give us a volume, right? This term right here is the volume. And I like to use a V with a bar through it because we're going to have a speed. We're also going to have nu, which looks kind of like a V, and then we're going to have volume. So I'll use V with a bar through it to hopefully make it clear that that's volume. And so that term is volume. So if I take this expression and I divide both sides by the volume, then what I get on the left is a collision rate per unit volume. And the collision rate per unit volume, that's what we define as the collision rate density. Collision rate density. It's the number of collisions per unit time per unit volume. And notice that the volume here is going to cancel that. So it is just equal to the product of I and our total macroscopic cross. So like in terms of the units for collision rate density, we're saying that it's collisions. So it's a number of collision reactions, and it's a rate density. So it's per unit volume and it's per unit time. And the units on both sides should match. So we already know that the units of the macro cross section are more complete. Thinking about it is that it's the number of reactions per the neutron distance traveled. Expected number of reactions per neutron distance traveled is the macro cross-section definition. And then based on what we have on each side, we can think about what the units of I we should expect. And here, those units are going to be neutron centimeters per centimeter cubed per second. Because if the neutron centimeters up top cancel the neutron centimeters on the bottom, then we have the same units that we would expect for the collision rate density. So this right here is kind of like an alternative or like a slightly different expression or maybe way of thinking about the neutron intent. Oops. This is like a different way of thinking about what the expression for the neutron intensity is, that it's a path length, neutron path length per unit volume and per unit time. So I want us to think about, does that interpretation make sense? And the way that we can do that is by considering this kind of simplified case where we have one energy neutrons bouncing around in some volume. If we use n, little n is the symbol for the neutron density, little v as the symbol for the neutron speed, dv for the control volume, and dt for the time interval, then we can use these expressions to think about what's the total path length, like what's the path length made by all of the neutrons in this little cube. And that's going to be the path length of one neutron times the number of neutrons that are there. So if I want to know how far does one neutron go, it's going to be its speed times the time interval, right? This path length is going to be the speed times dt. And then the number of neutrons there is the neutron density times the volume. If I multiply the neutron density by the volume, that gives me the number of neutrons. So this right here is the total path length. And I want a path length rate per unit volume. So that means that I want to take both sides and I want to divide by the time interval and I want to divide by the volume. Because if I do that, now on the left-hand side, oops, I've got path length rate per unit volume. And so notice that the dt's cancel and the dv's cancel. So this path length rate per unit volume looks like the product of n and v, the neutron density and the neutron speed. And we give that a name, we call that the scalar flux. So that is n times v. And that right there is where we will stop. And I think that's a good stopping point. Admittedly, we didn't get as far as I wanted to. It's the first lecture for me, so my pacing is going to be a little off. But this gives me an idea about how many slides about I can get through in a lecture. I also did the syllabus, which took like 20 minutes. So we will pick up here next time. If y'all have any questions, please let me know. And if not, thank y'all for your time and have a great day and see y'all next time. Yeah.
Will the dates put more possibly, change around depending on how far we get?
Yeah, it will. I'll let you guys know. I don't anticipate that being a problem for the first one because it's a lot of review. But I'll know that more like by Thursday, you know. Well, they don't necessarily go in order. So like no, so I guess I meant in terms of like the problems too. And also like a lot of that stuff is review. So like just because we haven't talked about Q value yet, you've seen Q value in other classes. So those are things that you could probably do even though we haven't talked about it. And I guess that's another thing I just want to stress is that I can't cover every single thing that's in the notes in class. So just because I don't cover it in class doesn't mean that it's not like that you're not still responsible for it. But as a teacher, I am going to try my best to make sure that we cover as much as we can.
I did miss it, but I don't think I got added to the Google Drive.
Oh,
Would
okay.
you like me to send you an email?
Yeah, if you could send me an email, that would be great.
Definitely, and I'm Jay.
Hey,
Thank
nice to meet you.
Uh,
Okay, yeah, if you could send me an email, that'd be great.
I'm Thomas.
Hi, Thomas.
I won't be able to make it to the Friday stuff because I'm.
Gotcha. Okay, well,
So I asked if you
that's,
were-
I see. I'm sympathetic to that, so I'll see what I can do. But yeah, just the format, it might be challenging.
Thank you.
Thank you.
Hi, I'm
Hello.
Shmobi. I was gonna.
What's your name?
Shmobi.
Jamobi?
Shmobi.
Jamobi.
Yeah.
Nice to meet you.
Nice to meet you. I was gonna ask about the Google Drive because I'm on it, yeah.
Okay, would you mind sending me an email and I'll make sure you get added to it?
Right here.
Yeah, it's, Simonian, that's like Simon. Oh, there you go.
Okay, thanks.
Mhm.
And are you gonna post like the build and stuff?
Yes, yeah, I will make sure that these get posted on the Google Drive.
Okay. And the report?
Yeah, I have, this is my first time doing the Zoom recording, so I have to double check how that works. I might end up providing like a link for you to access those somewhere, but I'll make that available to you in the next couple hours. You're welcome.
My name's Bert.
Hey, Bert.
Nice to meet you.
Nice to meet you.
So I'm doing fish camp this summer and I would
Okay.
probably start second exam might be when I have fish camp. And that's like, that could definitely be a later problem.
Yeah.
But, I was wondering if I might have to take like a day out or something like that.
Yes,
That's
if you're not gonna be here in class, definitely let me know in advance and I can schedule you a time to, yeah, take it.
Okay, I'll send you an email once I for sure know the date and then I'll let you know.
Sounds good. Thank you.
Josh,
Hey, Josh.
I have the same issue with the Google Drive. You just wanted to send you an
Yeah,
email.
that would be great.
Okay, cool.
Yeah.
And then, do you work at the lab that's off University?
No,
or-
I'm here. I'm
okay.
downstairs. M104 is in the is downstairs.
Okay, yeah, I asked because I work at Dr. Hassan's lab.
Oh, okay,
And so
cool.
I know Dr. Kimber has like.
Gotcha. Yeah,
an
we have
area
no
there.
experimental funding right now,
Gotcha,
so we're
gotcha.
basically not there.
Are you guys trying to get experimental funding? Okay.
Yeah.
Might see there eventually. who knows?
Sounds good. Yeah,
Thank you.
hopefully. See ya. Hello, Jake. Nice to meet you. Oh, okay. Yeah.
I had a question for exams and midterms and whatnot. Do you prefer to do like, if we have extended time for accommodations, do you
Oh.
do it personally or do I just set up in a time with the testing center?
Yeah, so if you have, did I get an email about the accommodations?
I
or-
was waiting. I didn't
Okay.
know if they were gonna send them out today for
Gotcha.
the accommodation
Okay.
letter.
I see, yeah, because when I get the accommodation letter, I'll read through it and I will propose how we can handle all of those different accommodations. So if it's extended time, yeah, I'd probably just do it in the testing. Well,
Just do it.
I'd probably just do it in the
Center.
testing center.
Yeah, I just didn't know, cause some I know know some professors and instructors will do it, set a different time.
Gotcha. Yeah, I think I already have, I think the testing center is probably preferred. Yeah.
I just want to make sure of that, and then, I want to, sorry,
No worries.
having to retake this class, and I just finished, radiation detection, so that's why I was.
Oh, okay.
asking a bunch on.
About the content scattering and
photon,
stuff,
Yeah,
yeah.
and all that, and that's what I was trying to.
Yeah, thank you for the questions
how
because it keeps me on my toes.
Compare, well, that's why I was trying to make sure I didn't want to make it sound like I was asking stupid questions.
No,
but-
no, it was a good one. Yeah,
Because neutrons, you figure like covering that class.
right. Yeah, Mariana doesn't even think neutrons are real, so why would we
As it
cover it?
says,
Yeah.
neutrons suck. They aren't, but now we have to do a whole class. But that's why, I was asking about the linear attenuation coefficient and whatnot,
Mhm.
but so with fission, neutrons produced with fission, do we ever count the spontaneous fission of the source?
Okay, so that's another good question. Usually we'll separate it out, like, if we have, if we write like change rate equals gains minus losses. Usually within the gains, I'll kind of break it up as, vision production. And then I'll also have like a source term. And so that source term is more like spontaneous vision, like California 252 or something like that. So it's, the reason that we separate them is because this is a decay reaction, whereas this is like it's like a new sigma times the flux. It's like a reaction. Yeah, I have that in these are the slides that were slides. Yes, because like you can assume it's a nice swelling. I recognize the position of the light just. There's a couple problems where it's like, whenever you get like an expression for the multiplication factor, you can ask questions to slash and so like, if there's some delta of how does that affect it?
Yeah.
Yeah, and the cold is like, it's because it's simplifying the sector. Usually what we end up doing is, I guess it depends on like where you find the data. It might be for a big target or, but if they don't specify, then you kind of have to. It's kind of, it's a big difference. I don't think I'm gonna. Okay, would you mind sending me an email? Because I set up a group, but I've never done the groups before, so they could just. Okay, send me an email. Okay, sounds good. Thank you.
So at this point, just.
Oh, you're all not in there too?
I can't tell, so I'm gonna go check and double check and make sure, but
Okay.
if not, because I got an email from you, so I don't know if that was also.
Interesting. Okay.
My Google Drive, check, share drive.
Okay, so I'll. check
Okay,
it.
yeah, double check that because it could be that it's just, it shows up in the share. Yeah.
Okay. So I disclose.
Okay.
The memory. But I usually work it pretty well. I'm just giving you a heads up as a professor, that's why I kind of sit up front,
Sure.
but I may be a little, ask a lot of questions. that
If you have questions, I really appreciate it. So yeah, that's no problem at all.
Perfect.
Hey, John.
It's really cool. So testing center, you said?
Oh, so yeah, if you have like the accommodations, this is my first time teaching here, so the way that it's worked so far is a student had accommodations from the accommodations people that were sent to me, that was like the list of, these are the things that we need to make sure is handled in the class. So if I get that list of accommodations, that's the first step in my mind, and then I will respond to that. I'll let you know for each of these accommodations, this is how I plan to respond to it, and then depending on what those accommodations are, we can work that out. But yeah, I need that thing from the accommodations.
Usually they send it to you.
Yeah.
We ask for it to be sent to you, so. we
Gotcha.
give it to them.
Okay.
think they don't do that till start classes, so I would assume.
Gotcha. Okay, yeah, I wasn't sure because I had already gotten one from somebody like a week ago or so, but yeah, that's all good, and I'll make sure that that gets taken care of.
Do you have like a general idea on if you're just gonna be having a separate room for like, people that need like the extra time or just,
It'll depend on the accommodations. I will probably just end up doing testing center, but I think it'll depend.
Okay.
Yeah, I think right now probably just assume testing.
Thank you.
You're welcome.
Thanks, Mary.
Marianne, no worries.
All right, have a good one.
Thanks.
So much.
For sure. Y'all take care.
You too.
Thank you.